this is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this video, we are going to determine the velocity of the block at the extreme positions and the equilibrium position. Study the curves of the mechanical energy, the kinetic energy, and the elastic potential energy versus abscissa. Study the curves of the mechanical energy, the kinetic energy, and the elastic potential energy versus time. Write the expressions of the kinetic energy and the elastic potential energy as functions of time.
Values of V at the extreme positions and the equilibrium position. An object of center of mass G performs simple harmonic motion. The abscissa of its center of mass is equal to xm sine omega 0 t plus phi. So the algebraic value of its velocity is equal to x prime equal omega 0 xm cosine omega 0 t plus phi. At the extreme positions, or when x equal plus or minus xm, using this equation. When x is equal to plus xm, then sine omega 0 t plus phi is equal to plus 1. And when x equal to minus xm, sine omega 0 t plus phi is equal to minus 1. So at the extreme positions, sine omega 0 t plus phi is equal to plus or minus 1. But we know that when sine alpha is equal to plus or minus 1, then cosine alpha must be 0. Using the expression of V, when cosine omega 0 t plus phi is equal to 0, then V is equal to 0. Therefore, at the extreme positions, the speed of the object is equal to 0. Let's watch this short animation. As you see, at the extreme positions, the speed of the block is equal to 0. Now, at the equilibrium position, or when x equals 0, observe the above equation. When x is equal to 0, since xm cannot be 0, so sine omega 0 t plus phi must be 0. Then, at the equilibrium position, sine omega 0 t plus phi is equal to 0. But we know that when sine alpha is equal to 0, then cosine alpha is equal to plus or minus 1. Now, going back to the equation of the velocity. When cosine omega 0 t plus phi is equal to plus or minus 1, then the algebraic value of this velocity is equal to plus or minus omega 0 xm. But we know that omega 0 xm is equal to the maximum speed of the object. Then, at the equilibrium position, V equal plus or minus Vx. Now, what do you mean by plus Vx or minus Vx? Let's watch this short video. As the center of mass of the block passes through the equilibrium position and moves along the negative x-axis, the algebraic value of its velocity is equal to minus V maximum. And as the center of mass of the object passes through the equilibrium position and moves along the positive x-axis, the algebraic value of its velocity is equal to plus V maximum.
Now, let's move to the curves of energy versus abscissa. You know that our system is a horizontal elastic pendulum in simple harmonic motion, where the block moves between minus xm and plus xm. The curves of energy versus abscissa are shown in this graph. Let's move to the mechanical energy. Our mechanical energy is constant, so curve A represents ME versus X. Let's move to the elastic potential energy. Now, to specify the curve that represents elastic potential energy versus abscissa, we will focus on two positions. In the first method, we will go to the position x equal 0. So, when x is equal to 0, what is the value of the elastic potential energy? Replace x in the expression of EPE by 0, and the answer is 0. Now, in the graph, which curve has a 0 value at x equals 0? It is curve B, which represents EPE versus X. Let's move to method 2. In method 2, we will focus on the extreme positions of the block. So, what is the value of the elastic potential energy at the extreme positions? We replace X in this expression by plus or minus Xm. And the answer is 1/2 kxm squared, which means that the elastic potential energy is maximum. Now, which curve has maximum values at the extreme positions? It is curve B, which represents EPE versus X. Now, let's move to the kinetic energy. You know that the expression of the kinetic energy is 1/2 mv squared, but here Ke is expressed as a function of the speed, but our graph is energy versus abscissa, so we can't use this expression. We must move to another useful expression. Ke is equal to me minus EPE. This is going to be Ke is equal to me minus 1/2 kx squared. Now, Ke is expressed as a function of x, so we can use the graph. Again, we will use two methods to specify the curve that represents kinetic energy. Again, we will focus first on the equilibrium position. So, replace x in the above expression by 0. You will get Ke is equal to me. Now, which curve has a value equal to me at x equals 0? It is curve C. So curve C is for Ke. Let's move to method 2. In method 2, we will focus on the extreme positions. When x is equal to plus minus xm, what is Ke? Again, replace x in this expression by plus minus xm. This is going to be Ke is equal to me minus 1/2 kxm squared. But 1/2 kxm squared is the maximum value of EPE, which is equal to me. Then Ke is going to be 0. So which curve has a 0 value at the extreme positions? It is curve C, which represents Ke versus abscissa.
Focus, please. This is important.
Now, curves of energy versus the time t. The first graph shows the abscissa x of g as a function of time, while the second graph shows three curves. One of these curves represents the mechanical energy, and one represents the elastic potential energy, and one represents the kinetic energy, and each as a function of time t. As you know, in simple harmonic motion, the mechanical energy of the system remains constant. By referring to the second graph, curve A remains constant with time. So, curve A represents the mechanical energy versus the time t. Now, let's move to the elastic potential energy. At t0 equals 0, the elastic potential energy is equal to 1/2 k x 0 squared. By referring to the first graph, at t0 equals 0, x is equal to xm. So, the elastic potential energy at t equals 0 has a maximum value. By referring to the second graph, we notice that the energy corresponding to curve V has a maximum value at t equals 0. Therefore, curve V represents the elastic potential energy versus the time t. Now, let's move to the kinetic energy. At t0, the kinetic energy is equal to 1/2 mv0 squared. But at t0 equals 0, x of 0 is equal to xm. Since x has a maximum value or equal to its maximum value at t equal to 0, so at t0 the speed of the block is equal to 0. So the kinetic energy of the block at t0 is equal to 0. By referring to the second graph, the energy corresponding to curve C has a 0 value at t0 equals 0. Therefore, curve C represents the kinetic energy versus the time t. Now compare or observe the two graphs. The abscissa x starts at t equals 0 with its maximum value xm, and then x decreases to minus xm after a time of 1 second, and then increases to x maximum after a total time of 2 seconds. So the natural period of oscillation of G is equal to 2 seconds. Now observe the curves in graph 2. The elastic potential energy starts at T0 equals 0 with its maximum value, and then this energy decreases to 0 at an instant 0.5 second, and after that it increases and attains its maximum value again after a total time which is equal to 1 second. And we observe that this curve repeats itself every 1 second. Similarly, the kinetic energy starts at T0 equals 0 with its minimum value which is equal to 0, and then this energy increases and becomes maximum at t equals 0.5, and after that it decreases and becomes 0 again after a time of 1 second, and it also repeats itself each 1 second. So the curves of the elastic potential energy and the kinetic energy are periodic and having a period which is called T energy equal to 1 second. By comparing the period of the energy and the period of oscillation of G, we can conclude that the period of the energy is equal to 1/2 to the natural period of oscillation of G. Expressions of the elastic potential energy and the kinetic energy versus the time t. If the abscissa of G is equal xm sine omega 0 t plus phi, and we know that the elastic potential energy is given by this formula, which is equal to 1/2 kx squared. Now replace x by xm sine omega 0 t plus phi in the expression of EPE, so we get a relation between EPE and the time t, which is equal to 1/2 kxm squared sine omega 0 t plus phi squared. Now let's move to the expression of the kinetic energy as a function of time. We know that the kinetic energy is given by 1/2 mv squared. So to write the expression of the kinetic energy as a function of time, we have to find the expression of V as a function of time. V is equal to x prime. So V equal omega 0 xm cosine omega 0 t plus phi. So replace V by omega 0 xm cosine omega 0 t plus phi in the expression of Ke. We get the relation between Ke and the time t, so that Ke is equal to 1/2 m into omega 0 xm squared times cosine omega 0 t plus phi squared. Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.